Okay, so we're getting into minimization today, and this is one of the two problems that I said that you had to tweak a bit to get to the simplex algorithm. The other one is when the origin is not feasible, and that's going to be something that I'm going to leave to somebody else. Those are like big M problems or a double shift kind of game there. So we're just going to stop here with minimization problems. If I'm doing a minimization problem, I'm minimizing some objective function. We'll call it W is j equals 1 to n c j x j, subject to some constraints. And what makes these constraints slightly different is that it's still a system of inequalities, but now they're all in the greater than situation. So now we're actually constraining upward instead of downward because it's a minimization problem. Okay, so this is the first idea. Like right off the bat, the origin isn't feasible in a minimization problem. So this can't immediately be put into simplex, and the constraints are all going the wrong way. So if you just try to build the slack variables from this, you would end up with negative slack variables, which is not something that simplex is going to like. So what we're going to do here is we're going to let's take an example. So let's take the example where I'm minimizing 12 cents on x1 plus maybe a cost of 15 cents on x2, subject to that x1 and x2 have to be greater than or equal to 300. 12x1 plus 6x2 has to be greater than or equal to 36. 10x1 plus 30x2 has to be greater than or equal to 90. And both x1 and x2 are strictly positive. Okay, so what we've got here is the idea that these three lines are bounding some unbounded feasible region, but we have that the minimization is going to be somewhere at its edge. The key here is something which is going to be called the von Neumann duality principle, which basically says that for every minimization problem in linear programming, there is a dual maximum problem. And that basically if you solve that maximization problem, you will automatically get the solution to the minimization problem. So let's look at how does this work. Okay, so if I wrote my minimization problem as like a simplex matrix without the slack variables and without making the bottom row negative, I would get 60, 60, 300, 12, 6, 36, 10, 30, 90, and my objective function is 0 0.12, 0 0.15, 0. Okay, so what I'm going to do is I'm going to transpose this matrix. Okay, and when I transpose it, columns become rows. So the first row becomes 60, 12, 10, 0 0.12, 66, 30, 0 0.15, and then 300, 36, 90, 0. Okay, so this now I can use to formulate my dual maximization problem. So I would maximize z is equal to 300 y sub 1 plus 36 y sub 2 plus 90 y sub 3. So I'm getting that from here. Subject 2. Okay, so my first constraint would be 60 y sub 1 plus 12 y sub 2 plus 10 y sub 3 is less than or equal to 0.12. And 60 y sub 1 plus 6 y sub 2 plus 30 y sub 3 is less than or equal to 0.15, such that y sub 1, y sub 2, y sub 3 are all greater than or equal to 0. So the argument here, according to von Neumann, is given this maximization problem, if I solve it, then the z value of this maximization problem will be the w value of the minimization problem. And in fact, if I read the solution matrix the right way, I'll actually know the position for x1 and x2. So let's look at how that actually works. Okay, so if I put the slack variables in, my problem looks like maximize 300 y1 plus 36 y2 plus 90 y3. Right, and then I get, oops, don't do that yet. Subject to 60 y1 plus 12 y2 plus 10 y3 plus s1 is equal to 0.12, and 60 y1 plus 6 y2 plus 30 y3 plus s sub 2 equals 0.15, such that y1, y2, y3, s1, and s2 are all greater than or equal to 0. Okay, so the initial matrix for the maximization problem, which is the dual, right, would be 60, 12, 10, 1, 0, 0.12, 60, 6, 30, 0, 1, 0.15, and then I need my negative 300, negative 36, negative 90, 0, 0, 0. Okay, so this is the matrix that I'm actually going to apply Simplex to, and I'm going to look at the end result after doing all of the pivoting. Okay, so let's look at what that final tableau looks like. So if you put that matrix in, you're going to get this as your result: 0.25, 0, 0.025, negative 0.083, 0.0018, and then you're going to get 0, negative 0.30, 1, negative 0.05, 0, oops, 0.05, 0.0015, and then the bottom row 0, 12, 0, sorry, 0, 12, that's fine, 0, 12, 0, 3, 2, and 0.6600. Okay, so the z value and the w value for both the maximize and the minimize problem is 0.66. Now this thing maximizes, let's see, this would have been x1, x2, x3, right? Or no, x1, x2, yeah, x3, s1, s2, or these were y's in the max problem. Oops. In the max problem, these were not x's, they were y's, so that's y1, y2, y3. So if I look at it, here's the two quiet rows. y1 is equal to 0.0018, y2 is equal to 0.0015, and z, not y2, y3, right? The other quiet row is y3. So we get 0.6600. So this is the solution to the maximization dual. I don't care about this, right? Because what I'm trying to solve is the minimization problem. Now, I could go and reverse this entire problem and see if I can pull an answer out of this, but realistically, here's the trick. S1, the value at the bottom of the S1 column is the X1 for the minimization problem. S2 is the X2 for the minimization problem, and this is the W. So I am minimized at 3, 2, and the minimal value is 0.6600. All right, so that's actually my solution. So you actually read the solution completely off the bottom row of the maximization problem. So basically what our slack variables in one problem are the what do you call it? The control variables in the other. So let's walk through one more of these kind of at a more brisk pace and see if we can't understand what's going on here. Okay, so let's try to minimize W equals 7x1 plus 2x2 plus 6x3 subject to 2x1 plus 2x2 plus, minus x3 is greater than or equal to 3, x1 plus 3x2 plus 5x3 is greater than or equal to 1, 5x1 plus x2 plus 2x3 is greater than or equal to 2, all positive. Okay, so let's write the dual. Okay, so this is a minimize, right? And this is a maximize. Maximize. Z is going to come from these three values. 3y1 plus y2 plus 2y3. So these three values give me the three values for my objective function. Okay, so the constraints, you read them going down. Right, so this is subject to 2y1 plus y2 plus 5y1 or y3 is going to be less than or equal to, and then I use these numbers as the constants, so that's going to be 7, 2y1 plus 3y2 plus 1y3 is less than or equal to 2, and then negative y1 plus 5y2 plus 2y3 is less than or equal to 6, where y1, y2, y3 are all greater than or equal to 0. Okay. So if you don't trust my work there, actually build the matrix and transpose it, and you'll see that it comes out exactly as we say. So the simplex matrix is based on this maximization problem. So across this I should get, see I got three constraints, I'm going to need three slack variables. So it's 2, 1, 5, 1, 0, 0, 7, 2, 3, 1, 0, 1, 0, 2, -1, 5, 2, 0, 0, 1, 6, and then -3, -1, -2, 0, 0, 0, 0. Okay, if I use the simplex algorithm on that matrix, I get this really ugly reality with lots of fractions. 0, -1/2, 1, 1/4, -1/4, 0, 5/4. I get 1, 7/4, 0, -1/8, 5/8, 0, 3/8, 0, 31/4, 0, -5/8, 9/8, 1, and that's 31/8, and then 0, 13/4, 0, 1/8, 11/8, 0, 29/8. And if I've been attentive to this, it's really, really easy to see what's going on here. So this is going to be x1, this will be x2, this will be x3, and that's w. So I minimize at 1/8, 11/8, 0, and w is equal to 29/8. So that works out. Note the maximization answer would be like x1 is equal to 3/8, x3 is equal to 5/4, and z is 29/8. And the slack variable here still exists. Alright, so that's it. This is how to do minimization. You first find the dual, and then you minimize. So there you go.